of this video is to walk through how we would program a full adder in Verilog. Now, where we'd started was we had the half adder implemented, and that's shown over here. And we talked about how you can take two bits, X and Y, and form a sum bit with an exclusive OR and a carry out with an AND to form a half adder. All right, the difference between a half adder and a full adder, once again, is that a full adder has both the two sum bits, X and Y, but also a carry in bit, which in this case is labeled Z. All right, so if you want to build an even bigger adder, you take full adders and cascade those together to get a ripple adder. So that's where we're heading with this. Okay, so notice that we've already written the code for the half adder, and to remind you of where we are, we have a box here that forms the schematic. So the inputs are labeled X and Y, and we have the outputs S and C. All right, so from Mano, here's the circuit that we're trying to implement. We talked about this in the lecture and proven that this gives you the result that you want for a full adder, gives you the right truth table. Okay, so I've redrawn this here into a form that's easier for us to use for programming the Verilog modules that combine the two half adders. All right, so this is an important concept where we start with an instantiation of a half adder. Okay, so there's the first one, and that corresponds to this point in the Mano circuit. And then we put another instantiation, half adder 2. All right, so those are shown. And then we show explicitly what the inputs and the outputs would be so that we can use those when we write our code to connect everything together. We need to be real disciplined about this so that we'll know what connects to what. All right, so you see here, this is our circuit. So we have the inputs X, Y, and Z. So we'll need to define those. And then you'll see we have wires that connect different things together. We'll have to put that into our Verilog code to get to our final output. All right, so let's get started with writing the code. All right, so the first thing we know is that we're writing a module for the full adder. So we type in module, and then we are going to give it the input and the output list. So I open a bracket and close a bracket so that I can start my list. All right, so I have inputs X, Y, and Z, and then the outputs are S and C. All right, so in this particular case, you know, the inputs and the outputs for the half adder and the full adder are named the same thing. That's okay, we can keep them straight from the context, but that's going to matter whenever we instantiate the two half adders. All right. So the next thing we notice is that we do have some wires that are going to connect things together, so we should define those. So we can put wire, and I'm seeing SW1, CW1, and CW2. All right, so we'll use those wires, and then let's instantiate the two half adders. So to instantiate, we use the name of the module, and then we're going to use two different labels so that, you know, we have two unique versions of the half adder. So half adder 1 and half adder 2. All right, so those go in parentheses, and then we give it an input list. All right, so we're passing things by reference so that we don't have to worry about the order. It gives you a little more documentation of what's going on, and it's less error prone because you don't have to get the inputs and the outputs in the exact right order. All right, so I know I have an input X. All right, so that's why I draw these diagrams. Dot X is the input on the half adder module, and that's connected, looking at the diagram, to X. All right, moving on, dot Y is connected to Y. And then we have output dot S connected to SW1. All right, you see how we're using that. Dot S was the output of the half adder. SW1 is what we connected it to. All right, and finally, dot C, the dot means that's the thing we're connecting to by reference. All right, or by name, and the output is CW1. All right, so there's the half adder instantiation. I close this bracket, and I've got the first one done. All right, the second one, HA2, the same thing. We have .x as the input, but you notice it's connected to the wire SW1. All right, so that's why that diagram is useful. And then .y is the other input, that's connected to Z. The output of the second half adder, all right, we've got HA2 labeled, so .s is connected to output S, as it's shown in the diagram. And .c from the second half adder is connected to CW2. All right, so we're almost done, but then we need to assign the output to this OR gate. All right, so we need to assign C is equal to CW2, and our OR symbol is just the vertical bar. So CW2 ORed with CW1 gives us the last part of the full adder. And then we've started this module, we need to end the module. All right, so hopefully you've followed along and been able to follow the steps, and you see the importance of this diagram, and you're learning about Verilog and how this can be useful to instantiate designs.